So, okay, with that, we get to our last talk, which is our second keynote by Professor Kishor Trivedi from Duke University. The title is Accelerated Life Testing Applied to Software System. So Kishor Trivedi holds the Fitzgerald Hudson Chair in Department of Electrical and Computer Engineering at Duke University, Durham, North Carolina. He is the author of a well-known text entitled Probability and Statistics with Reliability, Queuing, and Computer Science Applications. Dr. Trivedi is a life fellow of the Institute of Electrical and Electronics Engineers. Dr. Trivedi is the recipient of IEEE Computer Society's Technical Achievement Award for his research on software aging and rejuvenation, and recipient of IEEE Reliability Society Lifetime Achievement Award. So with that kind of very brief introduction of Dr. Trivedi, I just, let me,
well, I'd like to thank the organizers, Hamza and Alex, for inviting me. And I did not know I was doing load testing, but they convinced me I'm doing load testing. So this talk, actually, the core of this talk I've never given before. So I worked very hard, but I built it around the stuff I know very well. And I know the stuff I'm talking about here also well, but primary work was done by a postdoc on the accelerated life testing. But I've provided the background of why this is important and why this was possible. So with that, let me start the talk. And it would have been lovely to be in Rennes, where my old friends like Remo, Marie, and so on are there. But unfortunately, I'm stuck in Durham, like you are all stuck in your places. So the outline of my talk is, after some motivation, I'm going to introduce a phenomena that some of you may have heard of and some of you may not have, called software aging. And that will give rise to the notion of environmental diversity and software rejuvenation, which will then bring me to the possibility or need for accelerated life testing. Accelerated life testing has been used very extensively in the hardware systems, but what we have done is adapted that to software systems. And the very first example was actually one of my former postdocs, Rivalino Matias Jr., in Brazil, having done that as a part of his PhD thesis. And I was attracted by it. And so I invited him to be my postdoc for several years. And we have subsequently worked on that. So it's very interesting to apply this notion of accelerated life testing to software systems. That's where I want to get to. But in order to get to that, I have to build up a lot of other stuff that is also very interesting. So first observation is that there are too many failures and downtimes in practice than we like. And within that, if you explore further, we find that hardware is not the major cause. Hardware fault tolerance, hardware fault management are relatively well known. But the system outages tend to be more and more due to software failures. So we have to concentrate on software failures. Now, to corroborate my point, this chart I borrowed from my friend at Alcatel-Lucent, Mina Mendiretta, that shows that portion of downtime due to hardware is 13% in their experience and 65% due to software failures. And you can also see in the newspapers advertised downtimes, Google, Amazon, more from Microsoft, Google. So these examples indicate that even the most advanced tech companies are not offering highly reliable software that we expect them to. So before we go on, I want to make a very clear distinction between the notion of fault, error, and failure, because oftentimes a lot of confusion is created by the wrong use of terminology or different use of terminology. This is the terminology I would use, that failure is said to occur when the delivered service no longer complies with the expected service. So either a wrong output is delivered or no output is delivered. That is a failure. And failure may be caused because some bits in the system state are wrong. So error is that some bits in the system state are wrong, and the cause of the error is the fault or the bug. So a fault or a bug in the context of software, bug is a fault. So a fault or a bug may give rise to errors if exercised by the right set of inputs. And that by itself may not be a problem until the error propagates to the output to cause a failure. So fault may cause an error, which may cause a failure. So keep this distinction in mind. It's very important in order to go further. Okay, so what we have decided is that, at least in my context, I have decided the software is a bigger problem than hardware. And so what do we do? What do we do to try to get reliable behavior from software? So the first idea that comes to mind to people is that you use good software engineering practices so that number of faults that you have in your software is very small. But we have found that in large complex software systems, however hard you try, faults are going to be there. So the next thing that you try to do is test and debug and find as many faults as you can and remove them. But in spite of all the testing that we do, we find that the software that we delivered in practice is never fault-free. There are lots and lots of bugs in large software systems in practice when they are used in operational state. So the next, deployed software contains many bugs leading to failures during operation. So, and yet what we want is failure-free system operation, even with software. So key challenge then is to have reliable software operation, given that the software that we are operating on is buggy. And so a possible solution is similar to what hardware people have considered fault tolerance or redundancy, that is, use more components than necessary. So similarly, should we not use software fault tolerance to be able to have reliable software operation given buggy software? So in the classical software fault tolerance, people pondered over this issue in the 1970s, and they decided that the nature of fault tolerance in software systems would be different from that in hardware. They thought that it does not make sense to use identical copies of software for fault tolerance like we do in hardware. In hardware, we use identical part numbers to back each other up for fault tolerance. But if you do that in software, they made the decision that it doesn't make sense because they have exactly the same bugs. So if one copy of software fails, the second copy is also going to fail. And so, so they decided that it is better to do something that they call design diversity. Software fault tolerance then is based on the use of design diversity. What is design diversity? Design multiple software versions to the same specifications. And that you can ensure that by using different algorithms, different programmers, different programming languages, different development testing methods. By whatever methods you choose, you produce multiple versions to same specifications. And we want to make sure that these multiple versions are as independent as possible from the point of view of bugs. They have different bugs. And then there are multiple ways of employing the design diverse versions of software that you have produced. Two principal versions. One is called recovery block, which came from Newcastle upon Tyne, and N-version programming, which comes from UCLA. N-version programming roughly corresponds to parallel redundancy, and recovery block corresponds to standby redundancy in the context of hardware. So given this, what we find that these methods, the classical techniques, are they sound very good, and they have published a lot of papers and a lot of books and stuff like that. But it is very rarely used because it's very expensive. it is already expensive to produce one version. Now you are asking me to produce multiple versions of software. So it's only in the safety critical, life critical applications these techniques are used. But we do need failure-free operation even in non-life critical, non-safety critical systems. So what we need is affordable software fault tolerance, not the software fault tolerance based on classical techniques, which can be called non-affordable or expensive. So what we have been advocating in my group is this possible answer, which we are calling environmental diversity. So I will have to explain to you what is environmental diversity. But before that, what I will tell you is a little bit about software aging. So let me describe to you software aging phenomena before I get into environmental diversity. So what is software aging? It is commonly believed that unlike hardware, software does not age. But since 1995, for sure, we know that software does age. And not many people may know, at least in this sense, but once I describe the phenomena to you, you will realize it's, oh, yes, I know that. So in physical hardware systems, this behavior is well known, and there is this bathtub curve, the failure rate, early life followed by useful life, followed by wear out phase. This is the aging in the hardware context. Whereas software aging is the name given to a phenomena that is empirically observed in many software systems, that as runtime period of the system or process increases, system slows down or its failure rate tends to increase. You often see this, isn't it? And then, unlike hardware, there is no physical or chemical deterioration in software. The software appears to age, or it behaves as if it is aging. There is no real aging. And what constitutes this aging? The deterioration of the application process's internal state. And it is caused by cumulative effects of successive error occurrences. The notion of error accumulation is essential for characterizing the software aging phenomena. And software applications running for a long period of time exhibit this degradation with respect to usage of system resources, like increasing failure rate, decreasing performance, and eventually leading to system failure. And this is due to bugs in applications, operating system, or software libraries. And this has been observed in just about every major software system, Windows, Solaris, Linux, Android, you name it. And most every system is subject to this kind of behavior. And for that, we define the notion of aging related bug, ARB, and the picture is very important. I was telling somebody in the morning that jokes are very rare in the Zoom sessions, unlike the real life session. So at least you might laugh, some of you might laugh at looking at this notion of a bug, aging related bug. So aging related bug is a bug that leads to an accumulation of errors, either inside the running application or in the system context environment, resulting in an increased failure rate or degraded performance. And the bug causing memory leak is the most typical example of this, but many other resources besides memory are subject to this behavior. And the picture of the fundamentals of aging, software aging, can be seen like this. This bug is sitting there somewhere in your software or operating system or whatever, aging related bug, and it may be activated under some aging factors. And when activated, it might cause error accumulation. And after enough error is accumulated, system might fail, or in the meantime, system is slowed down. And this aging is due to memory leaks, unreleased file locks, non-terminated threads, shared memory pool latching, storage fragmentation. There are many different phenomena due to which, after time passes, some of the resources of the system, operating system, seem to disappear in a black hole. And when the failure occurs due to any of the resources exhausting, the common recovery technique is to restart the process, reboot the virtual machine, or reboot the node, or fail over to an identical replica which has the same bugs. There is no design diversity, but identical replica, much like we do in hardware. So restart, reboot. We know that they have been around for a long time to deal with hardware transient faults. But do they help in dealing with failures caused by software bugs without actually fixing those bugs? And if yes, why? And so our answer is that this is due to environmental diversity. Environmental diversity. So what is environmental diversity? So reactive maintenance after a failure due to software aging applied after a failure occurs, process restart, VM reboot, OS reboot, failover to an identical software system. And the bug that caused the failure most often not removed, and yet on restart, we expect the system to work. System is expected to work after restart or reboot. And so why is this the case? Because environment of the application has changed. And what is environment? The operating system resources and other applications running concurrently. And underlying idea of the diversity, environmental diversity, is that these actions free up the system resources, like operating system resources, remove error accumulation due to round of errors and things like that. And so thus the environment where the application is executed has been changed enough and cleaned enough, leading to increased availability of OS resources. So this is environmental diversity. Now, first, let's model very quickly a simple semi-Markov availability model, including these failures due to aging-related failures. So system is up and running here, and due to a failure due to aging, it failed, and now the reactive restart or reboot has taken place. And so it is very easy to show in this case that the steady state availability of the system is given by mean time to failure divided by mean time to failure plus mean time to repair. And here the mean time to failure is mean time to aging related failure, and mean time to recover is due to restart or reboot or whatever. Now, in order to solve for steady state availability, I will need the mean time to repair or mean time to recover as well as the mean time to failure. So we need to obtain the time to failure data in order to be able to compute the mean time to failure and therefore compute the availability. So need for data is now coming in. Now, implications of aging is that we know that in the hardware context, hardware components of systems that are subject to aging, it is common to carry out preventive maintenance to improve its reliability or availability. So since now software is also known to age, preventive maintenance of a software system can be useful, and in this case, to improve reliability and availability. And it has been given a very sexy name, if you like, software rejuvenation. So software rejuvenation is a proactive or preventive maintenance in the context of software systems. And so now, once again, coming back to the notion of design diversity, which is a classical software fault tolerance technique, we know it's expensive, and yet we know need the affordable software fault tolerance. And so potential answer, second potential answer is that preventive maintenance based on environmental diversity known as software rejuvenation. So software rejuvenation is the next thing I will quickly introduce. It's a proactive technique to counteract software aging, to prevent or postpone failures and slow down performance degradation. It's a periodic proactive rollback to a clean state. And intuitively, the picture is given here. And the potential actions are garbage collection, defragmentation, flushing of kernel or file tables, application or service restarts, VMM or OS reboot, and so on. And once again, I would like to mention that we are rejuvenating the environment, not of the software system itself. And since there is overhead in carrying out rejuvenation, you don't want to carry out rejuvenation too frequently, and you don't want to carry out rejuvenation too infrequently, because then you are more liable to have a failure of the system. So determining the optimal schedule of preventive maintenance is important, particularly for 24/7 systems. And these ideas have been used in many systems in one way or the other, not necessarily optimally, not necessarily scientifically, but they have been used. They might not be calling software rejuvenation. So let's now model software rejuvenation. Same model shown earlier, but now with rejuvenation. So as earlier system is up and running here, it may fail due to aging-related failures, and this is reactive recovery. But every once in a while, we will trigger rejuvenation. This is a proactive action, and the proactive recovery is carried out here. So, for this particular system, now, if you know the distribution of time to failure, and if you know the mean time here and mean time here, then you can determine the optimal rejuvenation trigger interval delta. And the equations for, so the idea then will be to collect past times to failure data, TTF data, and fit the data to known distribution. IFR stands for increasing failure rate distribution, and Weibull is an example of that. Hypoexponential is an example of that. And then using the model in the previous page, you can find the optimal times to trigger rejuvenation, optimal preventive maintenance intervals, if you like. And for that, it turns out in detail, you need to solve a fixed point equation. And these equations are known. Several papers and books provide the equations. And if you want to know one of the books, the green book, my latest book, maybe not the latest, but one book that has these equations. Okay, so now, so we need to collect the data of time between failures, time to failure data, either for determining the availability without rejuvenation or determining the availability with rejuvenation and finding out the optimal times to schedule rejuvenation. So we need the data, okay? But the difficulty is that software aging failures are very difficult to observe experimentally. It takes a long time because the accumulation of aging effects usually are random and require long run times. Thus, collecting data for statistically significant predictions of software aging is typically a long-running task and may be unaffordable in many circumstances, particularly when you're dealing with highly reliable systems. So this is an important problem that prevents many experimental and analytic studies of software aging and rejuvenation from using representative parameter values. And so this is where we looked at the literature on hardware testing, where they had introduced the notion of accelerated life testing. So can we make the system behave badly in experiments, that is, fail more often than it would fail during its regular use? But of course, then we have altered the system, and therefore we need to fix it back to so that the original use case, original use situation, we get the time to failure fixed for that particular situation. So let's now briefly talk about the accelerated life testing. Originally, my postdoc provided a large number of slides on that, but I've instead decided to give you the framework and getting into the accelerated life testing a little bit later. And in a shorter way, I'm going to describe this, but if there are questions, I'm happy to answer them. So particularly in this context, it's called quantitative accelerated life testing, QALT. So what we are going to do is accelerate the occurrence of aging-related failures through controlled experiments. And since QALT was developed for physical or chemical systems, we need to adapt it to software systems suffering from aging. And this is not as well explored as it should be, it could be. There have been only, as far as I know, 3 cases, 3 papers where this was done, and all 3 of them are from my lab. I may not have fully explored the literature, but if there are more, please point them out to me. But anyway, let me describe what has been done. So quantitative accelerated life tests are used in several engineering fields to significantly reduce the time needed for testing to determine the time to failure distribution or mean time to failure of a system under test, SUT, system under test. So QUALT was designed to quantify the life characteristics, that is MTTF and distribution of TTF of a system under test by applying controlled stresses. So you stress the system more than it would normally be under the normal use case. Since the system under test is tested in accelerated mode or stressed mode, the obtained results must be properly adjusted. So lifetime data obtained under stress is used to estimate the lifetime distribution of the SUT for its normal use condition. So this is the key, that is mapping the results back to the original system. Intuitively, you can think of it like this. So suppose that on this particular line, your system is under normal stress, normal use condition. There is no extra stress. And suppose that the lifetime density appears like that. So the mode is here, mean is somewhere here or something like that, right? Now I apply some stress and study the system again. At stress level 1, suppose that the PDF changes so that it is moved to the right here. So the mean time is lesser, for example, mean time to failure is smaller. And I can apply further stress and mean time to failure is even smaller. So I'm not experimenting at this level, I'm experimenting at this level. And from these, I'm going to map it back to the original use condition, which I'm not able to measure because of the excessive time needed. That's the idea, all right? So the main components of accelerated life test plan are accelerated stress variable that you have to choose and the levels of utilization, the stress levels or load. And then the stress loading scheme, life stress relationship, there is connection between what happens at the high stress versus what happens at the no stress. The number of samples you have to experiment with and how to allocate the samples among the various stress levels. Now, so the key idea is then to accelerate the activation of aging-related bugs or faults by controlling the workload and the stress levels of the workload. And the system under test that was chosen for the very first experiment is an Apache web server, HTTPD. Somebody mentioned that in the previous talk, version 2.0.48. And it is known to suffer from software aging, mainly due to memory leaks. And we verified that the HTTP requests addressing the dynamic pages versus static pages cause memory leaks in this HTTPD version. And experiments we conducted, are there any questions? Chat? Okay, let's see. Okay, I'll reserve the questions to the end because it's hard to read at the same time and so on. So if you don't mind, ask me the question at the end, okay? So the experiments were conducted use page size as the stress variable. Given the dynamic pages, now different page sizes has a different stress on the system and has changes the time to failure. Okay, so this is the test bench, if you will. This is the node in which the Apache web server is installed, and this is the node from which the HTTP perf requests are being sent. And different health monitoring and measurement, HTTP size, and so on is done. So the main parameters of this particular experiment is that the aging factor was that the HTTP requests addressing dynamic pages rather than static pages. Stress levels were 3 different page sizes. Sample size was calculated from pilot sample failure times, and it will turn out to be 21. And test allocation procedure among the 3 different stress levels was equal So 7 experiments per stress level. And so this is the more details of the experimental plan. So 3 stress levels. So normal usage was 200 kilobytes of page size, all dynamic pages, remember? And then the 3 stress levels we experimented with was 400 kilobits page size, 600 kilobytes and 800 kilobytes. And since the 1/3 proportion of all the experiments, so 7, 7, 7. So 7 experiments like this, 7 experiments like this, 7 experiments like this. So far, so good? All right. To better control the exposure of, well, I'm going to skip this. This is more details of the experiment. And we measure the size, the resident set size of the HTTP processes after every 100 requests, of so many kilobytes per page, 400, 600, or 800. We consider the time to failure, not in the units of wall clock time, but the number of bunches of 100 requests processed before HTTPD crosses certain threshold. We can connect it to wall clock time if you want to, but our results are in terms of these hundreds of requests after which the process fails. So these are the results from those 7 experiments on each stress level. So you can see already that this is the 8,400 requests before system fails here. This is 2,000 requests before system by that system fails. So stress level has a significant effect on the time to failure, as you can see. So samples of times to failure were fitted to several different distributions, and the criteria, the standard criteria of log likelihood function or Pearson linear correlation coefficient, and we found that the viable distribution did a best fit for these 3 accelerated lifetime data sets. And these are the results. So with the stress level S1, the viable distribution we found was of first rank among all the 3 distributions we tried. Similarly for stress level 2, stress level 3. So viable is the best fit for all the 3 cases. And then these are the parameters of the viable distribution. We computed both point estimates as well as confidence intervals, if you like. And now this is the crucial thing. So this is the viable density function with 2 parameters, beta and eta. And now this is the connection between stress levels and the parameters of the distribution. What we assumed is that the beta parameter, the shape parameter, does not change, but the scale parameter changes with the stress level. And the function of the scale parameter as a stress level is given by this inverse power law. Inverse power law is one of the standard methods that people use in accelerated life testing in the hardware context. There are other methods, but we tried this one and it worked well. And so when we substitute this, we have the density parametrically in terms of the stress level. And this may be called IPL viable model. IPL stands for inverse power law. And from that, we can also compute the mean time to failure of the system as a function of the stress level. And we can also compute the parameters of these inverse power law. V and W are computed, are estimated here from the data. And we can also see on this fitting on a plot here. This is log plot, the mean time to failure versus the stress level, which is in terms of the kilobytes of page size. So this is the 400 kilobyte, 600 kilobytes, and 800 kilobytes. On the log scale, it's a line. So that's what the inverse power law is. And in order to evaluate the accuracy of the estimate, we ran the experiment at the 200 kilobytes case also, the normal use. In this particular case, we could carry out the experiment. And we found that the observed value of the mean time to failure at the normal usage rate, 200 kilobyte page, is fairly close to the estimate from our model using the inverse power law. We can also go off and compute what is the speed up that we are gaining by using this technique. And after the details, we find that the experimental time was reduced by a factor of 7 by using this technique that of accelerated life test in this case. So what we can say, so we have applied this same idea and published in 2 other papers, more recent ones. This is in 2014 in ACM Journal of Emerging Technologies and Computing Systems. And very recently in Transactional Reliability, in actually a different context, in the context of what we call Mendel bugs or data race failures. So to conclude this talk, research in software aging has been limited to measure aging effects without observing failures, mainly because the long period of time required to observe aging-related failures. And we have demonstrated the feasibility of applying quantitative accelerated life tests to reduce the time to failures in systems suffering from software aging. And we use the concept of aging factors as stress variables, which enables the use of qual to software systems. And the selected references from which I have drawn this talk, there is a fairly recent book that we have published, edited book, Handbook on Software Aging and Rejuvenation. This is the state of the art right now on this very important topic, I think, of software aging and rejuvenation. My previous book I mentioned as giving the equations for computing the optimal rejuvenation trigger interval is published with Andrea Bobbio. This is called the green book. By the way, this is called the orange book. If you know, each of my book goes by the color of the cover. Accelerated life testing, it's a very well-known technique in the hardware context. And this Nelson's book is recommended for knowing more about the accelerated life testing. And as I mentioned, the very first paper that I observed was published by Rivellino Matias Jr. out of his PhD thesis on this topic of using accelerated life tests in the context of software systems. And I brought him over to Duke, and then we published more detailed paper based on that work in ISSRE 2010. And subsequently, he has also applied accelerated degradation test, which is related but different from accelerated life test. And then this is the paper that we published together with a visitor from China at the time in my lab. And then more recently with Kun of Behang University, who just recently finished his PhD thesis, a couple of papers of applying this idea to a slightly different context of Mendel bugs, which are environmental related bugs. We have applied this technique fairly successfully. So I'm hoping that the notion of aging related bug, Mendel bug, rejuvenation, and using accelerated life test in the context of software systems will get more popular, and more people will use these ideas and connect with performance testing, load testing, and so on. With that, I will terminate and stop sharing so that I can see faces. And if you want to ask questions, fortunately, in this context, people cannot throw eggs and potatoes or tomatoes or whatever. And I was complaining in the morning that jokes are difficult in the Zoom setting, but at least I provided some smiles.
Okay, perfect, Kishor. Thank you. Let's give Kishor a kind of round of applause, virtual applause for the talk. Thank you. So I will start with the question, and thank you for being timely. Actually, we have like around 15 minutes to have questions. I'll start with the question in the chat first, and then we will get the question from the audience. Vina asked the question that, can you say anything about the application to microservice-based software? I guess the question is that by moving to microservice-based applications, how things are like better or worse in terms of applying this technique to increase the reliability.
I think the same ideas will apply, but I haven't done it myself, so I can't be sure. But I would love to work with somebody who wants to work with me on that, or they can independently look at the papers and work. But Rivalino Matias Jr. is a very, very good person to also collaborate with on this topic. He is in Brazil.
Right.
I can see Mark Smotherman sitting here.
Yep. I have another question in the chat, and then
is there.
To David and also Andre. The question from Andre that in your practice, the centrality pattern moves as the stress is applied, but the dispersion does not change in slide number 37. Is that what usually happens?
Hold on, Hamza, hold on. Can you look at me, because then only I can hear it. I'm not hearing properly. I need the lip movement.
Okay, yeah. Andre, can you talk about the question yourself?
Yes, I'd be happy to. I think it was slide 37 or slide 30.
Wait a minute. Hold on, Andre. Andre always asks very tough questions. So promise me that this is not a tough question. All right?
I don't think it's a tough question because I think you already answered it.
Okay.
My question is whether the dispersion pattern changes with the centrality. Your picture didn't show that, but I think the analysis you had on slide 50 did show that the dispersion changes as you increase the stress.
Well, so now if you in detail, you look at the model, the beta, the shape parameter was assumed same. It is possible that you can vary that too.
Okay.
And that's what you're referring to.
Yes,
now
exactly.
In the model, we have assumed that eta, the scale parameter changes, but the shape parameter does not change. I'm not sure that we are wedded to that. But in this case, we got good fits. But it is possible to consider beta also vary.
Okay, thank you.
Yep.
So this was not such a tough question. I expect you to only ask tough questions.
David,
and if you ask if you do ask a tough question, I have an answer. Good question. That's it.
Okay, I'm going to lower my hand now.
Always the fallback. As fascinated by all this, it's all really great. How do you determine what are the variables that are going to stress your system? To
very good question. Very good. That is a very good question, and it requires you to understand the system very well. And so, in this context, there is this paper that we have written called Fundamentals of Software Aging. So basically, whatever system you're studying, you need to understand the fundamentals of it.
Okay. Any other questions?
I could have said very good question, right? Since very good question.
Any other good question?
What I think I'm hoping that more people, I observed a lot of talks today, but no jokes at all. So I'm hoping that more people don't do that anymore. You know, it's okay on Zoom also to laugh a little. No more questions?
Yes, I have a question.
All right.
I don't know if it's going to be a tough one or not. A lot of concurrent programming problems occur because of pathological sequences.
Okay,
you
very
talked
good,
about the distribution. Can you say something about generating pathological sequences to provoke concurrent programming problems?
Sure, very good, very good, very good. So, I've introduced the notion of aging-related bug here, right?
Yes.
The other notion that I didn't introduce because of time is called Mendel bug or non-aging related Mendel bug.
Right.
So the idea is that there are some bugs in software that are so simple in a conceptual sense that they get excited or manifested only by the workload that is seen by the software system. On the other hand, there are many other bugs that are not so simple, and not only the workload, but the environment in which the software is operating participates in determining whether that bug will manifest itself as a failure or not. And the former bugs, the simple bugs, are now called Bohr bugs, named after Niels Bohr's simple atom model. And the latter bugs are called Mendel bugs, named after Mandelbrot, who brought us fractals. So Mendel bugs are elusive. That is, they do not manifest consistently in the same way every time under the same workload. Sometimes failure occurs and sometimes not under the same given workload. And such bugs, the environment, what is meant by the environment? Again, the same question was asked earlier is it, I forgot his name.
David, I think.
David. Yeah, David, yeah. So what is the environmental factors that are responsible for colluding with the workload to determine whether a failure will occur or not? And concurrency level will be one prime one, synchronization, concurrency level, etc. And so we have demonstrated in the paper, in 2019 paper, that for my school, I believe, or several other cases, that you can determine which factors are responsible for each bug in the specific case. But the jury is out. A lot more work is needed on Mendel bugs, how to test Mendel bugs, how to determine the factors responsible for Mendel bugs surfacing more intensely or less intensely. So there is a lot more work to be done, But there is some work.
Thank you.
Mm-hmm. But remember Mendel bugs, remember aging-related bugs, remember rejuvenation. These are the topics that performance people need to look at.
Not to be confused with a Heisenbug.
Heisenbug it was a misnomer. It was used by Jim Gray in his paper for what he should have called Mendel bugs. Okay. Heisenbug turns out to be a very, very small portion of Mendel bugs. Heisenbug is one that disappears when you try to find it. Okay. And not all Mendel bugs are like that.
Gotcha.
So unfortunately, Jim Gray in his famous paper made an error, and so that keeps propagating.
Okay, Vahid, please go ahead.
Hello, Kishor. Thank you very much for your presentation. This may be a little bit of a naive question, so I don't know. It definitely doesn't rank as a smart one, but you said that software aging issues are difficult to observe. I'm having kind of a hard time understanding why that is, because most resource depletion or saturation issues that I know are relatively easy to observe. It could be difficult to observe to find the root cause, but just to basically—
Very good question. Yeah, very good question. So I didn't say that it is difficult to observe. That is, the slowdown due to aging-related bugs is not difficult to observe. But the time to actual failure due to aging-related bug, it might take a long time. That's the difficulty in that sense. It might take a very long time.
But if you just simply observe it, then you can react to that. Is that not enough?
No, but that's the rejuvenation, yes. But when should you do the rejuvenation? So even for that, then you need to know information about so if you just want to do seat of the pants, yes, that's what happens all the time. People do seat of the pants. But what we are trying to do all through this conference, or people need to know the underlying mathematics so they can do better. As David said in the morning, just a little bit of math. It's not rocket science, very simple formulas. But if you do that, you do better. That's it. And most people in practice are using some form of rejuvenation without calling it that, and without following the science behind it and doing by seat of the pants.
So let me then ask this follow-up question: that, for instance, if I'm let's say interested in memory leaks, what would I lose if I just set a threshold on my memory consumption, and whenever I go past that threshold, I restart the process, software, or do rejuvenation?
Yeah. So once again, you might be doing it too frequently or not frequently enough, right? So how do you know? So if you want to follow the science there, you can do better. Now, how much better? You'll have to find out, right? I don't know. I can't tell you how much better unless and until all the measurements are made and all the mathematics is done.
So I guess that also goes back to the definition of failure, system failure, right? What do you define as? So
actually, what you are describing is rejuvenation. Rejuvenation can be time-based or condition-based. What you're talking about is condition-based rejuvenation. And within condition-based, you can set a threshold or you can predict. Yeah, after measuring, you can predict how long it will be before a resource will be exhausted, or you can simply set a threshold at which you do the rejuvenation. So all these are relatively well explored, and one source is that book, Handbook on Software Aging and Rejuvenation.
Oh, thank you very much.
Mm-hmm.
Okay. Any other question? We still have time for Kishor.
Yeah, when I was young, I used to run over my allotted time. As I got older, I make my talk shorter, so there is more time to discuss things.
That's perfect, actually. Very good. Do we have any other question? I myself actually have a kind of comment on this. With this new paradigm in cloud computing, like for example, serverless, with each request, at least in per request paradigm, the container or the function will be renewed for each request again and again. So it's just this rejuvenation, you have it per request. So how do you see that in case of, to just look at this paradigm as a kind of reliable paradigm in order to do computation? And maybe that's one reason that actually serverless computing getting like more and more attention these days because of this kind of inborn feature that it has.
Say that again. You have to explain to me a bit more.
In serverless computing, we just spin a new container for each request when we have it, and then the container will go on and working for like some limit time, and then when request is done, that will go down, and then with new requests we have a new instance, right?
So environment, it doesn't build up for one container, but the container is contained in an environment anyway, so you can't escape the environment.
Yeah,
so
you get it.
Level.
You get it regenerated, but I guess because we have this different layer of the ecosystem. For example, the virtual machine and the physical machine, you cannot rejuvenate them, right?
That's right.
So you still have that problem.
Yeah. So at the lowest level, there is some environment cleanup, but there is a lot more environment. So
exactly.
When you talk about rejuvenation, there are granularities of rejuvenation, right? So at some point, it'll catch up with you. It doesn't matter what you do, right?
Yeah, of course.
Current day aging is going to take place. Software aging is going to take place. There's nothing you can do about it.
Right.
All right, this was fun. I worked very hard on making this talk because at least the last part was not done earlier by me in any setting. And you should thank Hamza for that.
No, my pleasure to have you here. Thank you, Kishor, once again.
Thank you.
Yeah, actually, that would conclude our session today on LTB. So I would like to thank everyone again, all the speakers, very amazing talks, the panel, the papers, industry, and also research paper, of course, the keynote speakers. And as you know, the ICP just get started, we have all like other workshops like tomorrow and also ICP itself during the week. So I guess we will see each other on those like sessions again. And I don't have anything to add at this time. Alex, Peter, do we have anything to say or mention before we conclude? Okay.
Yeah.
We are good?
Yeah, and thanks everyone for joining, and thank you for making the workshop to have a very great program. Thank you very much.
Thank you, and we hope to post all slides and recording on the workshop website.
Yeah, we will update the website with the talk, with the slides and everything. So for later reference, that could be the reference. And last year in the Slack, I wrote that hopefully I see you next time in person. And again, you see that's the situation. Here we are, and hopefully next year that'd be the case for sure. Okay, everybody has a good day, and I'll see you around. Bye for now.
Bye.